Good evening, everybody. Today we'll be talking about lecture memory, and that will be covering our quick summary for lecture 10 in computer architecture with Professor Benjamin Schaefer. Without further ado, let's go ahead and get started. So, content slide over here shows what we'll be discussing over today. We'll be talking about introduction to virtual memory, addresses translation, paging and segmentation, as well as page tables and TLBs and what the differences between them. And then we'll also dig into some virtual memory benefits and issues and some examples and case study, and we'll then brief around these at the end. Without further ado, let's go ahead and get started. So over here, we have an introduction to virtual memory. So what is the concept behind it? The concept is just like virtual addresses and physical addresses. And they're usually another concept that we need to also address is the MMU, which is the memory management unit. So what are the functions of those? So virtual memory is just there for like to extend RAM with secondary storage that we spoke about in our previous lecture, and then also provide memory protection, as well as manage memory allocations and defragmentations. There's some historical context around it in early computers and embedded systems like the ones that were in the Intel 8086. And here to our left, we have just like um, a small example of what we'll be going over today. Just like this is showing a picture of a translation from a virtual address into a physical address and what happens to the 20-bit once it goes to the TLB. We'll dig further into this in our lecture today in the next slides. So over here, we'll talk about address translation. So the process, the CPU generates virtual addresses. The MMU is the one that translates virtual addresses to physical addresses. What's the mechanism behind that? It uses a use of page tables, who are shown over here to our left in our example. And then also a translation look aside buffer, which is the TLB, which is used as a cache for address translation. Now, address translation is done virtually, and address is and it's divided into page number and offset. Page number looked up in page table to get physical address. That's how it's done. So over here to our left, it just shows like how the whole thing goes on, the address translation, and the process behind it. So it goes from the processor onto the base, and then from there it becomes a physical address, which then is stored in our physical memory that we just talked about. And then we can look that up with page tables in our physical memory. Next over here, we'll talk about paging and segmentation. So what's the difference between them? So paging is pretty much for fixed size blocks, so like pages, and it simplifies memory management and may lead to internal fragmentation. However, segmentation is variable size blocks, not fixed sized. And then they're better at memory utilization and they're more complex in management, and they may lead to external fragmentation. So the difference between them is that the paging has a fixed size, segmentation is variable, and when it comes to fragmentation, paging is focused in the internal side, and then for segmentation, it's focused in the external fragmentation. The usage behind this is just used for modern system for paging, and then system use both for compatibility, just like the x86 architecture. Alrighty, without further ado, let's get over here to our next slide, which we'll talk about like page tables and TLBs. There's a couple of types of page tables. There's three types. There's a single, there's a multi-level, and there's an inverted page table. So the single page level page table, it actually is a maps virtual page numbers to physical page numbers. And the multi-level page table, it's a hierarchical structure which uses storage requirements. And for the inverted page table, it maps physical addresses to virtual addresses. Now, when it comes to single level page tables, they're simple, but their storage is a requirement. As for the multi-level, only top levels need to be in memory. Not every single one of them, just like the single level. And then for the inverted page table, it reduces storage, but it's more complex. Over here, as for TLBs, there's cache page table entries to speed up and add up address translation, and there's TLB hit versus TLB miss hit. So over here, we have a multi-level paging in an operating system showing over here to our left in our example. showing the virtual addresses going from different levels into an offset as well. And then from an offset, it creates a physical address. Okay, now virtual memory and the benefits and its issues. What are the benefits of having a virtual memory? It has a larger address space than a physical memory, the memory protection isolation between processes, and it's also simplified memory management for programs. So virtual memory is actually very beneficial compared to our secondary memory and our primary memory that we spoke about earlier in our lectures in the semester. However, there's of course some issues that fall under virtual memories. So the issues can be like page faults and their handling and how much they can handle and how many physical addresses they can store. And the performance also impacts, and it can impact the TLB and cause misses and page faults. And think about it too is that they have a limited lifetime of flash memory in embedded systems. Next over here, we'll just be looking at two examples. Systems with 64-bit virtual addresses, 43-bit physical address, and 8 KB pages, and to calculate VPN and PPN sizes. There's a way we can calculate those for the 64-bit virtual addresses, and that would have to require for us to convert that virtual address into a PPN and then calculate their offsets, and then from there we'll be able to calculate their sizes. Over here also we have the TLB hit rate of 95%, miss penalty of 150 cycle. Well, to calculate average address translation times, that will require to have some more percentages and calculate the penalty as well. So that way we are able to calculate an average address translation. As for the case study, the comparison of demand paging and swapping, and then we're also required to know the impact on performance and memory management of the virtual memory. Next over here, we'll just talk about virtual memory and implementation. There's a demand paging, swapping, and protect mechanisms. So demand paging is pretty much, it load pages only when accessed, and it's efficient use of memory. As for the swapping, it moves entire programs between memory and disk, and it's useful for system for limited RAMs. However, for protection mechanisms, it ensures isolation and security between processes, and it uses also permission bits and protection levels. Over here to our left, we have a what is pretty much a diagram showing what is a demand paging in an operating system and how it works. And where this saves as seen over here, it gives from the CPU, goes into a paging tables, then promotes a address, and from there it goes to a main OS operating system, and then from there it goes to a secondary memory, and from secondary memory it goes back to our main memory or primary memory, and then from there goes back once again to our page table and then back to the CPU. That's how demand paging works. Alrighty. So just a quick conclusion and a summary of what we did today. The key concepts are just virtual memory and address translation, benefits of the virtual memory we went over, and why can they be helpful compared to also like secondary and main memory, and then the importance of virtual memory as it enables efficient memory utilization and provides essential memory protection. And then future directions for this, it would be advancement in more management techniques and probably integration of faster storage technologies to avoid any issues and faults that can happen in current virtual memories. That would do it for today. That was lecture 10, which was covering virtual memory, and I'll catch you guys next time. Thank you.